Welcome to Advanced Learning Tutoring. This is the chemistry playlist. Please like this video and subscribe to our channel. Atomic structure, key terms. Atoms. All substances are made up of atoms. An atom is the smallest part of an element that can exist. Protons, electrons and neutrons are the subatomic particles that make up an atom. Elements. There are about 100 different elements that exist. They are shown in the periodic table. An element is made up of only one type of atom. Compounds. Compounds are formed when elements react in a chemical reaction. Compounds contain two or more elements chemically bonded. The chemical bonding is either ionic or covalent. Chemical reactions. Chemical reactions are when atoms are rearranged to form new products, whereas physical reactions are a change of state, for example, evaporation or condensation. An example word equation is hydrogen plus oxygen forming water as the product. Mixtures. A mixture consists of two or more elements or compounds not chemically combined together. An example being the air. The air is made up of nitrogen, oxygen, carbon dioxide, and small amounts of other gases. The chemical properties of each substance in the mixture are unchanged. Mixtures can be separated by physical processes such as filtration, which is the removal of a solid from a liquid using a filter funnel and filter paper, crystallization, which is the evaporation of a solvent and allowed to cool to form crystals. Simple distillation evaporates first and then separate the liquid by boiling points, then cooling to condense and collect each fraction separately. Simple distillation can be used to separate mixtures that are liquids. Fractional distillation is very similar to simple distillation, but contains a mixture of many more substances. Again, evaporating to separate the mixture by their boiling points, cooling to condense. Paper chromatography separates mixtures due to samples' solubilities. Solubility is how well a particular substance dissolves in a solvent. The model of the atom. Through time, different scientists have different theories on what the atom consists of. John Dalton described atoms as solid spheres. This was incorrect due to solids being defined as particles that are closely packed together. An atom, being a single atom, cannot then be described as a solid. J.J. Thomson developed the plum pudding model. His measurements of charge and mass showed that an atom must contain even smaller negatively charged particles called electrons. The plum pudding model showed the atom as a ball of positive charge with electrons embedded in it. Later, Rutherford developed a gold foil experiment. Positively charged alpha particles were fired at a sheet of gold. Most of the particles passed through empty space, but a few were deflected, concluding there must be a central area of positive charge, now known as the nucleus, due to particles being deflected, and a cloud of negative electrons surrounding the nucleus due to most of the particles passing straight through. Niels Bohr developed the nuclear model, following on from Rutherford's gold foil experiment, suggesting electrons orbit the nucleus at specific distances in shells. Experiments showed the nucleus can be divided into smaller particles, which gave the same charge as the hydrogen nucleus. This was the work done by Rutherford. James Chadwick later discovered neutrons. His experiments provided evidence for existence of neutral particles and helped with the understanding of isotopes. The subatomic particles are the proton, neutron, and electron. The relative charge and the relative mass are in comparison to each other. The relative charge of a proton is +1, the relative charge of a neutron is 0, and the relative charge of electrons are -1. The relative mass of a proton and the relative mass of a neutron are both 1, and the relative mass of an electron is approximately 1/2000th of the mass of a proton or neutron. Therefore, the mass of an electron is very small and said to be 0. Why atoms have no overall charge? In an atom, the number of electrons is equal to the number of protons in the nucleus. Electrons are negatively charged and protons are positively charged. Therefore, the same number of opposite charges will cancel each other out. Therefore, atoms have no overall electrical charge. The number of protons in an atom of an element is its atomic number. All atoms of a particular element have the same number of protons. Atoms of different elements have different numbers of protons. The size and mass of atoms. The radius of an atom is approximately 0.1 nanometers. 1 nanometer is 1 × 10⁻⁹ of a meter. The radius of the nucleus is approximately 10,000 times smaller than the radius of the atom. The sum of the protons and neutrons in an atom is its mass number. Atoms of the same element can have different number of neutrons. These are called isotopes. Relative atomic mass. The relative atomic mass of an element is an average value that takes into account the abundance of the isotopes of the elements. Abundance is how common that particular element is. An example, calculating the relative atomic mass of chlorine. Chlorine has 2 isotopes, chlorine-37 and chlorine-35. Both have 17 protons. Chlorine-37 has 20 neutrons and chlorine-35 has 18 neutrons. The abundance of chlorine-37 is 25%, which means 25% of all chlorine atoms are that of chlorine-37, and 75% of all chlorine atoms are chlorine-35. To calculate the relative atomic mass, you multiply the mass number of the isotope by the abundance, and you repeat for the number of isotopes, dividing this number by 100 to give you the relative atomic mass. Therefore, for chlorine, we do 37 × 25 plus 35 × 75. Divide this number by 100 and you get an answer of 35.5, which is why we see the mass number of chlorine in the periodic table to be 35.5 and not a whole number. Electronic structure. Electrons in an atom occupy the lowest available energy levels. In the first shell, closest to the nucleus, can hold up to 2 electrons. The second shell holds up to 8 electrons, and the third shell holds up to 8 electrons. If we look at the electronic structure of sodium, it has the atomic number 11, therefore we have 11 protons and 11 electrons. We feel 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the third shell. Periodic table. The elements in the periodic table are arranged in order of atomic number, or proton number, and so the elements with similar properties are in columns known as groups. Elements in the same group in the periodic table have the same number of electrons in their outer shell, and this gives them similar chemical properties. Chemical properties are how the elements react. The development of the periodic table. Before the discovery of protons, neutrons, and electrons, scientists attempted to classify the elements by arranging them in order of their atomic weights. The early periodic tables were incomplete, and some elements were placed in inappropriate groups if the strict order of atomic weights was followed. Mendeleev left gaps for undiscovered elements and in some places changed the order based on atomic weights. Metals and nonmetals. Metals react to form positive ions by losing electrons. Nonmetals react to form negative ions by gaining electrons. The majority of the elements are metals. Metals are found to the left and towards the bottom of the periodic table. Nonmetals are found towards the right and the top of the periodic table. Some common properties of metals are that they conduct heat, conduct electricity, are malleable, which means they can be bent into shape, sonorous, which means they produce a ringing noise when tapped. Some properties of nonmetals include not being able to conduct heat or electricity. Group 0, the noble gases. Elements in Group 0 are known as the noble gases. They are unreactive as they have a full outer shell of electrons. Therefore, they do not need to lose or gain any electrons. The boiling points of the noble gases increase down the group as the strength of the intermolecular forces increase. Group 1. Elements in Group 1 are known as the alkali metals. They have similar chemical properties due to the single electron in their outer shell. When they react, they want to lose this outer shell electron. Going down the group, the alkali metals become more reactive as the outer electron is more easily lost. The outer electron becomes further away from the nucleus due to the increased number of electron shells. Therefore, the attraction between the outer electron and the nucleus decreases. Going down the group, the melting and the boiling points decrease. The alkali metals are soft, they can be cut with a knife, and they have a low density, typically floating on the surface of water. The reactions of the Group 1 metals. Reacting Group 1 metals with water, they react vigorously and produce hydrogen gas and metal hydroxides. For example, sodium reacting with water will produce sodium hydroxide and hydrogen gas. Hydroxides are salts that dissolve in water to produce an alkaline solution due to the presence of the OH-, the hydroxide ion. The more reactive the metal, the more violent the reaction. The observations we make when a Group 1 metal reacts with water are that the metal will float on the surface and dissolve, effervescence or a gas being released, and occasionally flames being released. Reactions of Group 1 metals with chlorine. Group 1 metals react vigorously when heated in chlorine gas to form white metal chloride salts, for example sodium chloride. The observations we make in this reaction, having a Group 1 metal, typically silver and shiny, reacting with chlorine gas to produce a white metal solid. Reacting the Group 1 metals with oxygen. You can burn the Group 1 metals in air containing oxygen, and they react to form a metal oxide. For example, sodium plus oxygen forms sodium oxide. Group 7, the halogens. The halogens have similar chemical reactions as they all have 7 electrons in their outer shell. They consist of molecules made of pairs of atoms known as diatomic molecules. For example, when we find fluorine at room temperature, its formula will be F2 as it's diatomic. They all have 7 electrons in their outer shell, meaning when they react, they all want to gain 1 electron to get a full outer shell. Fluorine is a very reactive, poisonous yellow gas. Chlorine is a fairly reactive, poisonous, dense green gas. Bromine is a dense, poisonous, red-brown volatile liquid. Iodine is a dark grey solid or a purple vapour. The halogens undergo displacement reactions. A more reactive halogen can displace a less reactive halogen from an aqueous solution of its salt. For example, chlorine plus sodium bromide will produce sodium chloride plus bromine. This is because the chlorine is more reactive than bromine. Going down group 7, the reactivity decreases. This is due to the increased number of electron shells as you go down the group. Fluorine is more reactive than chlorine. This is because the incoming electron to make a full outer shell is closer to the nucleus in fluorine than chlorine. Therefore, the negatively charged electron is more attracted to the positively charged nucleus in fluorine due to being a shorter distance, and therefore the outer electron is more easily gained in fluorine. The transition metals are the central block of metals in the periodic table. In comparison to the group 1 metals, the transition metals have higher densities, higher boiling and melting points, and higher strengths. Transition elements have ions with different charges. For example, iron can form +2 or +3 ions. Transition metals form coloured compounds and are useful as catalysts. Typically, we see the colour of copper 2+ compounds to be blue.